You sit at your kitchen table on a mid-July afternoon. Outside, the air is thick and heavy, shimmering with a dull, oppressive heat that makes the grass turn brittle and brown. Inside your home, there is a persistent low-frequency hum, the sound of a $5,000 steel box bolted to your outer wall, vibrating under immense strain as it forces chemical refrigerants through copper lines just to keep your living room tolerable. In your hand, you hold a $400 utility bill from the power company. We have been conditioned to accept this monthly tax as the inevitable price of modern comfort. We buy the complex units, we sign the seasonal service contracts, and we accept that in 10 or 12 years the compressor will burn out, and we will have to write another large check to replace it. It is a cycle of recurring expense and dependency that we rarely stop to question. But let us look at a completely different scene. In the summer of 1881, a Pennsylvania Dutch farmer named Jacob Stoltzfus took a 40-foot length of common clay pipe, buried it 4 feet beneath his wheat field, and ran the end straight through the thick stone foundation of his farmhouse into the root cellar. For the next 62 summers, he and his family sat at that same dinner table, without a single drop of sweat staining their cotton shirt collars, even on the stickiest August evenings. His neighbors called him eccentric when they saw him out there digging that trench. His grandchildren called him a genius. When the Pennsylvania Department of Agriculture finally surveyed that property in 1947, they recorded an indoor temperature of 61 degrees Fahrenheit on an afternoon when the outdoor mercury had climbed past 94. There was no electricity, no compressor, no chemical refrigerant, and no monthly bill. Just a buried pipe, a hole in the earth, and a principle of physics so quiet and dependable that the modern air conditioning industry has spent the better part of a century hoping you never look into it. I first felt this system myself several years ago while visiting an old order farmstead in Lancaster County. It was one of those suffocating Midwestern afternoons where the humidity hangs like a wet wool blanket. Walking across the porch and through the heavy oak door of the farmhouse, the shift in the air was immediate. It was not the aggressive, dry, chemical chill that hits your skin when you walk into a modern supermarket. It was a soft, deep coolness that smelled faintly of clean stone and damp earth. In the corner of the kitchen, partially hidden beneath a hand-braided wool rug, sat a simple cast-iron floor grate. If you placed your hand over it, you could feel a steady, silent draft of 62-degree air rising naturally into the room. There was no fan running, no switches flipped. The house was simply breathing. Before we go any further, stop and think about what this method actually is. And let us be entirely honest about its limitations. I am not here to sell you a fantasy or tell you that a length of plastic pipe will turn a thin-walled, uninsulated shed in the middle of a desert into a commercial meat locker. It will not. Understand this. The earth tube is a system of mitigation and natural balance, not a high-powered mechanical appliance. If your property sits in a low-lying swamp with a water table just 2 feet below the surface of the grass, this method will become a constant battle against moisture unless you install specialized drainage sumps. In regions with extreme stagnant humidity like the Deep South, the incoming air will drop its moisture inside the tube rapidly, meaning your construction geometry must be flawless to prevent dampness. But for the vast majority of households, this little-known solution can reliably lower your indoor temperatures by 10 to 15 degrees. While operating on less power than a common light bulb, the engineers call this an earth-air heat exchanger. The old-timers just called it an earth tube. The underlying science is incredibly simple, and it relies on public data that the United States Geological Survey has been recording for over a century. If you dig down between 4 and 8 feet below the surface of the grass, the temperature of the soil stays remarkably constant year-round. Across most of the country, that deep soil temperature holds steady between 52 and 57 degrees Fahrenheit, completely indifferent to what is happening on the surface. It does not care if there is a blistering heat dome over the plains or a 0-degree blizzard howling across the roof. The thermal mass of the planet acts as a massive, slow-moving battery that absorbs and buffers the seasons, delaying the summer heat by several months until it dissipates entirely. When you bury a smooth, horizontal pipe at that depth and leave one end open to the outside air, you create a natural heat sink. Air enters the intake at 90 or 95 degrees. As it travels those 40 or 50 feet through the pipe, surrounded by millions of tons of 55-degree earth, it slowly surrenders its thermal energy to the soil. What emerges into your living space is cool, breathable, filtered air. In 2019, researchers at Purdue University published a study verifying this exact setup in central Indiana. They took a 60-foot run of standard PVC pipe, buried it, and measured its output. The materials cost less than $70, yet the system produced the continuous cooling equivalent of a 1,200-watt window air conditioner. The system itself consumed absolutely 0 watts of electricity to cool the air. The only energy input was a tiny 35-watt inline fan used to draw the air through the tube and push it into the room. They calculated the seasonal coefficient of performance, which is just the technical term for how much cooling you get for the energy you put in, at somewhere north of 40. For context, a high-end modern central air system has a coefficient of performance of about 4. The buried pipe was 10 times more efficient than the complex machine the salesman tries to sell your family. Why do you continue to pay a utility company every single month for something the earth will give you for free? The answer is not a grand conspiracy. It is just simple commerce. No corporate entity can patent a hole in the ground. No one can sell you a monthly subscription to a length of pipe that you bury once and use for 80 years without a single moving part breaking down. The Amish understood this without needing a university laboratory or a peer-reviewed study. They figured it out by doing what traditional craftsmen have always done. They watched what worked, they threw out what failed, and they ignored the noise of the marketplace. In the original farmhouses, they did not even use that 35-watt fan. They relied entirely on what is called the stack effect, a simple rule of nature where warm air naturally rises. As the summer heats the upper stories and the roof of a house, that hot air escapes through an open attic window or a roof vent. As that warm air leaves, it creates a very slight natural negative pressure inside the lower levels of the home. That negative pressure gently draws the cool, heavy air out of the buried tube to replace it. The hotter the day gets, the faster the warm air rises, and the harder the system works to pull the cool earth air inside. It runs at noon, it runs during a midnight thunderstorm, and it runs when a regional power failure leaves your entire neighborhood in dark, sweltering silence. So, how do you take this principle and build it on your own land? How do you select the exact materials from a local hardware store for under $50? And how do you ensure you avoid the critical mistakes that lead to failure? To make this work for decades rather than months, you have to understand the specific geometry of the trench, the exact diameter of the pipe, needed to allow proper airflow velocity without losing the cooling effect, and the single most vital factor of all, how to handle the gallons of water that will condense inside that dark tube when hot summer air meets the cool underground earth. Let us look at exactly how to map out the trench, cut the pipe, and lay the foundations for a system that will cool your home for the rest of your life. Let us begin with the Friday evening trip to the local building supply yard. To do this right, you must ignore the modern aisle displays filled with motorized gadgets and complex digital controls. Your focus is entirely on raw, durable materials. You are looking for 10-foot sections of 4-inch or 6-inch diameter, smooth wall schedule, 40 PVC pipe. When you stand in the yard, do not let the clerk convince you to buy the flexible black corrugated drainage pipe just because it is cheaper or easier to lay in a curving ditch. Stop and think about this. The interior of that black pipe is full of deep ridges. Over the course of a humid summer, those ridges will trap moisture like tiny gutters, creating a stagnant environment where mold will eventually take root. The pipe you want is stark white, perfectly smooth on the inside, rigid, and emits a clear metallic ring when you tap it with your knuckles. Along with the pipe, you will need to pick up a few specific hand tools and adhesives. Pick up a can of purple PVC primer and a can of clear PVC cement. When you crack the lids on these cans later, the sensory feedback is immediate and unmistakable. The primer is a thin, vibrant violet liquid that smells sharply of sweet acetone and stains everything it touches permanently, while the cement is a thick, clear, viscous syrup that flows slowly off the brush. You will also need a handful of straight couplings, two 90-degree elbows for the ends of the run, a small roll of 24-gauge galvanized hardware cloth with a 1/4-inch mesh, and a stainless steel worm gear hose clamp. If you do not already own a standard handsaw with fine teeth, a tape measure, and a coarse half-round file, add those to your cart. The entire bill for these materials will sit somewhere around $50. Saturday morning is for the earthwork. Before you even touch a shovel or start the engine of a rented mini excavator, you must map the path of your trench. Walk out from the foundation of your home toward a clear, open area of your yard. Ideally, your line should run straight for 100 feet. Why 100 feet? Understand this, my own trials, along with the historical records of the old farmsteads, have proven that a shorter run simply does not give the hot air enough time to surrender its warmth to the earth, while a longer run creates too much friction, requiring a larger, louder fan to move the air. As you guide the machine to dig, look closely at the soil coming out of the ground. You will watch the color and texture shift dramatically. The top 12 inches are usually a light, crumbly brown, smelling of decayed leaves and roots. But as the bucket dips down past 4 feet and finally hits the 6 to 8 foot mark, you will reach the true native subsoil. In my region, this is a heavy, cold slate gray clay that comes up in dense, wet chunks. It feels slick and cool to the touch, even when the afternoon sun is beating down on your neck. This cold clay is your heat sink. This brings us to the single most critical step of the entire project, and the place where most beginners fail. The floor of your trench must be uniform and perfectly sloped. If your trench looks like a roller coaster with high spots and low spots, your system will fail within 2 seasons. Water will pool in those low dips, turn stagnant, and ruin the quality of your air. You must use a long carpenter's level to ensure the bottom of the ditch slopes continuously downward, away from the house, at a grade of exactly 1/4 inch for every foot of horizontal run. Over a 100-foot line, the far end of your trench will sit about 2 feet lower than the end closest to your foundation. Once the trench floor is graded, it is time to assemble the pipeline on top of the grass before lowering it down. Use your handsaw to cut the PVC sections cleanly. The friction of the blade creates a fine white plastic dust that smells slightly burnt and clings to your clothing. Use your half-round file to remove the rough plastic burrs from the cut edges. If you leave those burrs, they will catch dust and lint inside the pipe later on. Apply the purple primer to the outside of the pipe end and the inside of the coupling. Watch how it immediately dulls the shiny white plastic, softening the material so the weld can occur. Quickly follow with the clear cement. Slide the pieces together with a quarter-turn twist and hold them firmly for 10 seconds. You will feel a distinct wave of warmth pass through the plastic as the chemical reaction fuses the two pieces into a single, seamless conduit. Now, let us address the condensation relief system at the lowest, furthest point of the trench. Dig a small pit directly beneath where the final elbow will sit, about 2 feet wide and 2 feet deep. Fill this pit with clean, coarse gray river gravel. Before you connect the final vertical riser pipe that goes up to the surface, take a drill and place 3 half-inch holes into the absolute bottom of the horizontal pipe section resting over that gravel. This is your drainage valve. When the hot, humid summer air passes through the cold underground tube, moisture will condense on the smooth white walls, bead up into tiny drops, and run down the slope away from your house. It will drain out through these holes and percolate harmlessly into the gravel bed below, leaving the inside of your pipe dry and sweet-smelling. The far end of the pipe must now turn 90 degrees upward to form your intake riser. Bring this white pipe at least 24 inches above the final grass level to keep it clear of heavy rain splashes and winter snowdrifts. Take your sheet of galvanized mesh, wrap it tightly over the open top of the riser, and tighten the stainless steel hose clamp until it bites into the plastic. The zinc-coated wire feels rough and stiff under your fingers, but it is an absolute necessity to keep mice, wasps, and debris from turning your pipeline into a nest. Top this riser with a simple aluminum rain cap to keep out downpours. Position this intake in a permanently shaded spot, the northern side of a shed, or tucked deep beneath the canopy of a mature tree. Finally, bring the house end of the pipe through your foundation wall. If you have a stone or concrete basement, this requires a slow, rhythmic grinding with a diamond core drill, which throws off a fine gray masonry dust that smells of old lime. Slide the pipe through and pack the gap tightly with hydraulic cement, a gritty, dark gray paste that expands as it cures to form a watertight seal against groundwater. Inside the home, finish the pipe with a standard adjustable cast iron or steel floor register. Before you shovel a single mound of native dirt back into the trench, stop and protect your work. If you throw heavy clay and sharp rocks directly onto the bare PVC, the impact can crack the joints or alter your careful slope. Pour a 6-inch bed of fine masonry sand over the entire length of the tube first. It should be soft as talc, cushioning the pipe completely. Once the sand layer is in place, you can backfill the native soil, compacting it gently in 1-foot layers. Now, the project is complete, and the system is ready for its first test. Go inside your home, walk down to the register, and light a small stick of incense. Hold the thin, curling ribbon of blue smoke over the grate. If your slope is correct and the house is warmer than the earth, you will see that smoke instantly flatten out, caught by a silent, cool draft that carries the crisp, clean scent of a deep limestone cave directly into your room. You have bypassed the modern utility grid using nothing but a shovel, a length of white pipe, and the ancient memory of the soil. Let us step away from the physical work of the trench for a moment and look at the invisible forces that govern this entire system. To truly own a traditional craft, you cannot just know how to build it. You must understand exactly why it works, and more importantly, where its limits lie. If you do not understand the rules of the earth, you are just blindly copying a pattern, and that is exactly how mistakes happen. The underlying science here relies on two fundamental concepts: thermal mass and thermal lag. To understand thermal mass, let us look at a simple analogy from the kitchen. If you place a thin aluminum baking sheet over a flame, it turns searingly hot in a matter of seconds, and the moment you remove the flame, it cools back down just as fast. It has very little mass, so it cannot hold on to energy. But if you take a heavy, thick cast-train skillet and place it on that same stove, it takes a long time to warm up. It absorbs the heat slowly, stores it deeply within its dense iron walls, and continues to radiate that heat long after you have turned off the gas. The earth beneath your boots is the ultimate cast iron skillet. The sun beats down on the grass all through May, June, and July. But that heat cannot simply flash through the soil. The crust of the planet is an enormous thermal sponge, composed of millions of tons of tightly packed rock, mineral, and moisture. It takes months for the warmth of the summer sun to bake its way down into the deep earth. This brings us to the second principle, which is thermal lag. Because the soil absorbs heat so slowly, there is a massive time delay between the weather on the surface and the temperature underground. At a depth of 6 to 8 feet, the soil is completely out of sync with the calendar. The peak heat of a blistering July afternoon does not actually saturate down to that depth until late November or December. By the time that summer warmth arrives down there, the surface of the Earth is freezing, and the winter cold is starting its own slow journey downward. Conversely, the deep freeze of a bitter January blizzard does not fully penetrate to the 8-foot mark until June or July stop. And think about what this means. When you stand in your kitchen on a suffocating August afternoon and feel that cool breeze rising from your floor register, you are not experiencing some magical cooling effect. You are literally breathing air that has been cooled by the leftover remnants of last winter's frost, stored safely in the memory of the soil. It is a beautiful, slow-moving wheel of natural balance. But let us be entirely honest and objective about the boundaries of this method. The internet is full of folks who promise that an earth tube is a flawless miracle that works perfectly for everyone, everywhere. It is not. If you do not respect the specific conditions of your local climate and geography, you will waste your weekend and your money. First, consider your soil type. The efficiency of an earth tube depends entirely on the ability of the soil to draw heat away from the PVC pipe. Heavy, dense clay and moist loamy soils are magnificent conductors. They pack tightly around the plastic, leaving no air gaps, and their natural moisture content helps pull thermal energy out of the airstream rapidly. However, if your property sits on dry, loose, sugary sand, like the soils found in parts of western Florida, the Pine Barrens, or the high deserts, the system will struggle. Sand is full of microscopic air pockets. Instead of conducting heat away, dry sand acts as an insulator, trapping the heat inside the pipe rather than absorbing it. If you have sandy soil, a 100-foot pipe will not be long enough. You would need to double the length of the run just to get the same cooling effect that an Amish farmer gets from 50 feet of rich Pennsylvania clay. Understand this next point clearly. The water table is an absolute boundary. The design I showed you in the previous section, with simple weep holes draining into a gravel pit, relies on the assumption that your trench is dry. If you live in a low-lying coastal plain or a river bottom where the water table sits just 3 or 4 feet below the grass, you cannot use this passive drainage method. If you try, groundwater will push its way upward through those weep holes, fill your pipe like a drinking straw, and you will end up pumping stagnant pond water into your home. In high water table areas, the pipe must be completely sealed, submarine tight from intake to output. Any condensation must be managed from inside the house using an internal collection trap and a small mechanical condensate pump. The simplicity of the traditional design is lost, and the labor becomes far more technical. We must also look at the difference between what engineers call sensible heat and latent heat. Sensible heat is what you read on a standard thermometer, the actual temperature of the air molecules. Latent heat is the moisture carried by that air. An earth tube is a master at lowering sensible heat. It will drop 95-degree air down to 65 degrees without breaking a sweat. But when you take hot, humid air and cool it down, its relative humidity skyrockets toward 100%. If you live in a dry, arid climate like Arizona or eastern Colorado, this is a spectacular benefit. The air emerges into your home, cool and pleasantly comfortable. But if you live in the thick, swampy humidity of Georgia, Alabama, or the Mississippi River Valley, that cooled air will emerge into your living room at 70 degrees, but saturated with moisture. It will feel like the inside of a damp limestone cave, without a secondary way to strip that moisture out. Whether that means routing the air through a chamber filled with natural desiccant silica flakes, or running a small 30-watt mechanical dehumidifier indoors, the system will make your home feel clammy and can eventually cause dampness on your walls. The Amish in humid zones manage this by using very long, slow runs that force the moisture to condense completely inside the buried pipe before it ever reaches the house. But it requires absolute precision in the slope of the trench. Finally, you must look at the quality of the earth itself. If your home is built in an area with high concentrations of granite bedrock, your soil may naturally produce radon, an invisible, radioactive gas that seeps out of stone. A passive earth tube works by creating a slight negative pressure. If your pipe joints are not sealed perfectly, or if the plastic cracks during a minor earth shift, that negative pressure can draw radon gas out of the soil and pump it directly into your breathing air. If you live in a known radon zone, you cannot use cheap PVC seconds. You must use heavy-duty, continuous HDPE pipe, weld the joints with heat, and run a continuous radon monitor at your indoor vent. An earth tube is not a 5-ton mechanical air conditioning unit. It does not work by brute force, and it will not drop a poorly insulated, thin-walled house from 100 degrees down to 65 in 20 minutes. It is a system of gentle prevention, designed to maintain an equilibrium by running continuously. It is a partner to a well-built, insulated home, not a cure for a broken one. Now that you understand the science, the soil requirements, and the true limitations of the earth, we can turn our attention to the final phase, the fine-tuning of the airflow and the integration of the system into your daily living space. When you stand over a finished earth tube, listening to the soft, rhythmic sigh of cool air entering your home from the dark belly of the ground, you are not participating in some novel, experimental hack. You are taking your place in a grand lineage of human ingenuity that stretched across the continents long before the first electric grid was ever conceived. The modern world has a habit of viewing history as a progression from ignorance to enlightenment, assuming that because a technology is old, it must be inferior. But traditional crafts teach us a different truth. Our ancestors did not have the luxury of wasting energy, so they built in absolute harmony with the laws of nature. Stop and think about how the ancients survived the most unforgiving landscapes on Earth. If you travel to the arid deserts of modern-day Iran, you will find structures that are over 5,000 years old. Massive, beautiful mud brick wind towers known as badgers. The ancient Persian architects did not have steel compressors or electrical lines, yet they kept their vaulted brick palaces cool in the middle of 110-degree desert heat waves. They did it by pairing these high wind catchers with qanats, deep, underground water channels cut straight through the stone. The towers caught the hot, dry desert breeze high above the ground, funneled it downward through the earth, and forced it across the cold, flowing subterranean water before releasing it into the living quarters. The air that emerged into those ancient rooms was not just cool. It was washed clean of dust, carrying the sweet, crisp scent of underground stone. During the Middle Ages, the builders of northern Italy discovered a similar secret within the landscape. They noticed that certain deep limestone caves, which they called colvoli, maintained a perfectly uniform, chilled temperature year-round. Instead of trying to cool their stone villas by sheer force, they built magnificent interconnected stone ducts that ran from the mouths of these deep caves directly up into the floors of their grand estates, like the famous Villa Costozza. The natural pressure differences pulled the cold cave air upward, air conditioning entire palatial complexes, using nothing but the structural geometry of the earth. This is not folk superstition or rural myth. It is an unassailable engineering reality that modern science has spent decades quietly documenting. When the Department of Energy published its comprehensive technical reports in 1983, the data was clear. Earth-to-air heat exchangers were classified as highly viable, low-impact solutions for domestic climate control. The agricultural bulletins published by Iowa State University in the 1980s mapped out exactly how these tubes could keep livestock barns cool in the summer and prevent water lines from freezing in the bitter Midwestern winters, saving farmers thousands of dollars in operating costs. And as we noted earlier, the 2019 study by the researchers at Purdue University in the journal Energy and Buildings proved mathematically that this simple, Ancient arrangement outclasses the efficiency of modern mechanical appliances by a factor of 10 to 1. The documentation is sitting there on the library shelves, fully verified, just waiting for people to look at the ground beneath their feet. Understand this. The real barrier to this technology is not that it is difficult to build, but that it requires you to change the way you think about your relationship with your environment. The modern utility infrastructure wants you to remain a passive consumer, someone who sits in a sealed box, pushes a plastic button on a wall thermostat, and waits for a corporate entity to send a monthly invoice. It creates a state of fragile dependency where a single down power line or an oil price spike can throw your household into chaos. An earth tube is the exact opposite. It is an act of quiet, elegant self-reliance. It is a declaration that you have looked at your land, understood its natural patterns, and chosen to step off the treadmill of recurring expense. When you run that pipeline into your home, you are building an asset that will outlast the shingles on your roof, the vehicle in your driveway, and the very company that sends you your electric bill. A Schedule 40 PVC pipe, buried 6 feet deep in stable soil, does not corrode, does not rot, and does not rust. It sits in the dark, silent, and unchanging, doing its work for your children and your grandchildren, just as Jacob Stoltzfus's clay pipe did for his family over a century ago. So, this coming weekend, I invite you to do something real. Step outside onto your porch. Feel the heat of the summer sun on your skin, and then look down at the grass beneath your boots. Smell the dry, sweet scent of the parched summer earth. Realize that just a few feet below where you are standing, a vast, cool reservoir of 60-degree energy is waiting for you, completely free, completely stable, and entirely yours to claim. Walk the perimeter of your yard. Find that shaded northern spot behind the garden or under the oak tree where the intake riser could stand, catching the morning breeze. Picture the line of the trench cutting through the lawn, sloping gently away from your foundation. Think about the simple weight of a shovel handle in your palms, the clean snap of a handsaw through white plastic, and the sharp, sweet smell of the PVC cement fusing the sections together. It does not take an engineering degree or a small fortune to achieve this. It takes a single Saturday afternoon of honest, deliberate labor, $50 in basic hardware materials, and a willingness to trust the old ways of building. The knowledge has always been here, preserved by generations of practitioners who knew that true comfort does not come from a factory. It comes from the earth. The blueprint is clear, the physics are absolute, and the soil is waiting. Go out into your yard, dig the trench, lay the pipe, and let the earth breathe for you.